to section 6.4, using inverse functions. So up until this point, we've been working with simplifying radicals, working with exponential properties. We've been talking about how you do operations on functions, and we introduced the concept of a composite function yesterday. So now we get to this idea of an inverse function. What inverse functions are they are functions that undo one another. We're going to take a look graphically at inverses. We're going to look at equations, writing equations of an inverse. And there's some new notation here that we need to be familiar with. The inverse functions are going to be represented by this variable to the -1. It can be g to the -1, f to the -1, and that just is the notation we're going to use that refers to the f or the g inverse. That is not the same thing as on your calculator, your x to the -1 button, which is actually a reciprocal button. So these are not the same thing. When it comes to determining whether two functions are inverses of one another, this is the process by which we will do that. We will actually composite them into one another, and should the results both be equal to x, then we know that f and g are inverses of each other. We're going to take a look at an example for that later on. So just think of inverses are undoing one another. One example of this would be our equation for calculating Celsius and Fahrenheit. If you were to plug the Celsius equation into the Fahrenheit equation, or the Fahrenheit equation into the Celsius equation, you would undo the other one. In the concept of the graph components of inverse functions, if we know what the graph looks like, then we can simply switch the x and the y values of our original graph, f of x, and then we generate the inverse of this relation. So I can take any graph, switch its x and y's, and I will be creating this relation. It's called a reflection. And I can do this for any graph, but it doesn't necessarily mean that I have inverses. We'll get to that later on as well. So the graph of an inverse relation is a reflection. So there's that. We're going to talk about a mirror image reflection of the original function f of x over our line of reflection y equal x. So there's going to be our mirror line. We have different types of reflection. We have vertical reflections, which reflect over the x-axis, horizontal reflections over the y-axis. This reflection over the y equal x-axis is what we will use to talk about our inverse relationships. Equations for inverse functions. We do two things. We take the original f of x or g of x function, and we switch x and y, and then we solve for y. And when we solve for y, we'll be writing it with this notation. Inverse of x equals, and then our equation. Inverse of f of x equals. Okay, so those are the things to come here in the next couple minutes as we run through this. Let's take a look at the table of values, and graphically, how do we look at this idea of a reflection for a given graph. On the left-hand table, we have our original x and y values. On the right-hand table, we're going to be filling those in with the reflection of these 1, 4, 2, 5, 3, 6 coordinates. So we'll call this our original, and this is our reflected values. And we talked about that when we reflect, we simply switch our x and y. So let's look at the coordinates first. 1, 4. And here we are at 1, 4. And then 2, 5. And then 3, 6. So I have this dashed line here representing our equation y equal x. This is our line of reflection. reflection. So our mirror image will produce the same thing on the other side of that line. So what we do is we take our x and y values. So we take the x value of the original function. It will become the y value of our reflected function. And the y value of our original function will become the x value of our reflection. And that's the relationship we're going to generate. So 2, 5 becomes 5, 2, and 3, 6 becomes 6, 3. And now we can draw those points at those given coordinates. 4, 1, 5, 2, 6, 3, and we have the reflection. So this is our original, and this is our reflection. And there is this relationship when we're talking about reflections across y equal x. These points, the blue and the red points, are equidistant from that line of reflection. And we're connecting perpendicularly as well, right there. All right, so graphically speaking, that's the kind of thing we can do if we want to take a graph and draw its reflection. Just switch your x's and y values. What about the inverse equations now? Now this will be assuming that we actually have an original function that creates an inverse. We'll just get into the practice right now of doing our switching x and y and solving. Both of these examples, A and B so far, these are both linear functions, and linear functions do have inverses. So let's start with A. First thing we do is we switch x's and y's. So my y becomes an x. My x becomes a y. And then now we solve. Solve for y. So we're going to solve for y. And if I did that, I'd have that x minus 2 is equal to 4y. And then I would divide everything by 4. And we have y is equal to x over 4 minus 1/2 after I reduce. And then we'll go ahead, we can be writing it as the inverse is equal to x over 4 minus 1/2. So there's our inverse equation of y equal to 4x plus 2. And as usual, as we make our way through these example problems, feel free to stop and pause, try it on your own, and then check in with your answer. So switching x's and y's for this problem, this now becomes 2y plus 4x equals 5. Subtract that 4x, and 2y is equal to negative 4x plus 5. And now we'll solve for y. We get y is equal to negative 2x plus 5 halves. So there's our inverse function. So those functions didn't have any degrees other than 1, so now we get a cubic here. And the cubic function is a function that actually generates an inverse, so we're able to create an inverse equation here. So same old process, switch, and now solve. So x plus 4 is equal to 3y cubed. Divide everything by that 3. All right, just divide it all. And I can get y cubed is equal to the quantity x plus 4 all over 3. And then now we're going to undo this. And we get y is equal to the cube root of the quantity x plus 4 over 3. wanted to rationalize our denominator here, it's just the same thing as the cube root of x plus 4 divided by the cube root of 3. And I want to rationalize this with a cube root of 9. So I produce a cube root of 27 on the bottom. And what happens there is we get the cube root of 9 times x plus 4 all over 3. So that's an inverse function with our denominator rationalized, and then here is a rational expression underneath that radical. All right, so here we are practicing that verification that our functions are inverses of one another. Again, it's a matter of compositing one into the other, both producing the same result of x. If they produce different values, then they're not inverses of each other. We want them to produce this x value. So we'll try here. These two functions, again, both of them being linear, slope-intercept form. We do see that the slopes happen to be reciprocals of one another. But let's just see what happens when I composite f of g of x. Let's see, we see an f of, putting the g equation in, I would get f of 1/4 x minus a half. So we put that into our f function, and I get 4 times that 1/4 x minus a half. And then I still have this plus 2 that would happen on the end. Well, carrying through with our problem, 4 times a fourth is just 1, and 1 times x. And 4 times negative 1/2 is a negative 2. And then a plus 2, we see that those two cancel. And so we get an f of g of x is equal to x. That's good. Check the other one now. Create some space here. Now let's check g of f of x. So now we have g of 4x plus 2. So we get 1/4 times 4x plus 2 minus 1/2. Plugging into my g equation there. 1/4 of 4x, this gives me x, plus a half, minus a half, I get just x. So g of f of x is also equal to x. So with both of those, verifying they both equal x, so therefore our f of x and g of x are inverses. Alright. So trying that again with this one, you can try this one on your own real quick. Pause the video and come back and check. Here's what we would have. of the graphing component of this, and there is we're going to learn a way that you can very quickly tell based on the graph whether or not your function has an inverse. So here we have two graphs, one of them, both power functions, one of degree 2, one of degree 3. One of them has an inverse, and the other one does not. So if you look at the graph on the left, this is our quadratic. We have the original graph of f of x being our parabola, and taking a look at its coordinates, left 2, up 4, left 1, up 1, vertex is 0, 0, right 1, up 1, right 2, up 4. And then if I took each of those coordinates now, and I were to reflect them with our switching x and y, our negative 2, 4 becomes 4, negative 2. So this point becomes that point. Negative 1, 1 becomes 1, negative 1. And that point switches over here. 1, 1 becomes itself. And then 2, 4 becomes 4, 2. Again, see the reflection. So there we are, switching our x's and y's. Now, what makes this not a function is that if I were to conduct a vertical line test right here, anywhere through the red graph, we would see that I am intersecting the graph at more than one spot, which means no function. So even though we can create this reflection, that reflection does not represent an inverse. Whereas on the right-hand side, with a cubic function, so our original function is cubic, and I take all of those normal movements, which is a left 2, down 8, and a left 1, down 1, and a right 1, up 1, and a right 2, up 8, and I switched all of those, so left 2, down 8 became a left 8, down 2, putting me off of my graph over here somewhere. And then left 1, down 1 is the same thing. Right 1, up 1, same thing. Right 8, up 2, again, putting me off of my graph over there. I create that red curve. And now with this red curve, conducting vertical line tests, every time I draw a vertical line anywhere through that red curve, I do intersect just one time, and therefore we have a function. So what's the difference? Why did the parabola not generate an inverse, but the cubic did? It has to do with symmetry. The symmetry around that y-axis is what prevented our parabola from having an inverse function relationship. So if I have that symmetry around a y-axis, then I'm going to be in trouble with regards to an inverse. We have a couple functions that do have symmetry around our y-axis, one of them being parabola, of course, but then we also have our absolute value function would be the same case. All right, so that's one way to tell is once I draw my reflection, conduct a vertical line test to tell whether you have a reflection that represents an inverse. Now, if we wanted to take a look at quadratics, and we wanted to make sure that they gave us an inverse, then what we can do is what's called restrict the domain. So domain restrictions limit the values of x that we use for the function. And if you're specifically talking about a parabola, if I looked at just half of the parabola, I would see that I'd be able to turn that graph over with my switching x and y's and have a vertical line test work on that graph. So when we strip domains, what we do is we cut the graph in half essentially, and we decide do I want to look at the left side of the graph or the right side of the graph. So that's what's happening here. So those are called domain restrictions. And we can see a domain restriction in this example right here. We're restricting, so again, we have a quadratic of x squared plus 2. We're restricting this domain to say everything that is 0 and negative values only. So I'm looking at the left-hand side of the parabola. So first we're starting out with the original function. And if we remember things from our parent functions and our transformations, we know that this has a vertex of 0, 2. The graph is simply slid up the y-axis by a value of 2. And then if we were to use our normal parent function movements, we would say from 0, 2, I would go left 2, up 4, and left 1, up 1. And I'd have that. We're not seeing the other side of the parabola, again, because of this restriction right here. I don't see anything to the right of 0. So by doing that now, I'm able to now take those coordinates and then generate a reflection that shows me I have a inverse relationship. So a 0, 2 becomes a 2, 0, and a negative 1, 3 becomes a 3, negative 1, and a negative 2, 6 becomes a 6, negative 2, and we can see the relationship there. So there's that reflection between the red graph and the black graph across our line y equal x. All right, now that graph, that black graph, passes the vertical line test. So we have a function. And because we have a function, we have an inverse. All right, we're supposed to also find the equation of this. So let's see how that plays out with regarding the restriction on our domain. So we have our original function, f of x, which again is our y value, is equal to x squared plus 2. And we're going to make sure that we consider this x less than or equal to 0 part of our equation. We have to include this restriction when we write our new equation for our inverse function. Okay, so we go and we begin the process of switching my x's and y's. So now I get x is equal to y squared plus 2. And I'm going to also switch the restriction so that it says y is less than or equal to 0. So include those restrictions when you're writing the equations. Okay, we go and we solve this for y. So I get y squared is equal to x minus 2. At this point, I take a square root on both sides, and I get y is equal to plus or minus the square root of x minus 2. Now, the plus or minus, we will deal with that based on this right here. We can actually see the value that I'm supposed to use, positive or negative, based off of two things. Looking at the graph over here, we can see that all those y values for the black graph are below 0, which is what this is indicating, less than 0. How do I know if it's a plus or a minus? Well, if I'm less than 0, my radical is going to be negative only. So less than zeros are negative, we can get rid of that plus sign there. And then just take a negative square root of x minus 2. Now we're not quite done, because even though we come up with the equation, we still have a situation where underneath, so the radicand of our radical, we have to show what those limits of x can be. We have to restrict those domains as well. And again, physically looking at the graph, I can see that everything on that black graph has x values of greater than or equal to 2. Well, how can we figure that out? Very quickly, we know that underneath even roots, we have to have zeros or positives. So if I set that x minus 2 equal to 0, greater than or equal to 0, I would find that x has to be greater than or equal to 2. And that needs to become a part of my answer for my inverse function. So the inverse of x is going to be equal to negative quantity x minus 2, square root of x minus 2, with an x greater than or equal to 2 domain restriction. So my final answer for this, if I'm writing my inverse function, is negative square root of x minus 2 with the restriction of x greater than or equal to 2. That's just stating what my graph looks like. And again, if I look over here at that graph matches that description. It's got a start value of 0 and then down, or right 2. 2 is coming from this part. I'm inside the function, so it's a right 2 movement. I'm not moving up or down because I don't see a d value. And then I normally would have done right 1, up 1, right 4, up 2, right 9, up 3. But this negative out here is telling me to take all my up and downs and make them down movements. So right 1, down 1, right 1, down 1, right 4, down 2, right 9, up 3. So that equation generates that black graph. So you can have like multiple checks. Look at the equation. Does the graph match the equation? And then great way to verify that your inverse equation is correct as well. But please don't forget to include in these functions that start as power functions. We need to, especially if I start with the restriction on my domain, I need to include that restriction in my inverse equation as well. So let's try another one. So here we have another quadratic, and from our transformation, we know that my vertex is negative 2, 2. So I'm going to go negative 2, 2. And now this time you'll notice my restriction is based off of the axis of symmetry of that vertex. Because that's where the graph is going to be split in half, is at the axis of symmetry. So now it's saying, let's look at everything to the left again. Left of negative 2, so I go left 2, up 4 from there, and left 1, up 1 from there. And here's my original f of x function. Then we take all of those coordinates, and we switch them. So x's and y's. Negative 2, 2 becomes 2, negative 2. And negative 3, 3 becomes 3, negative 3. And negative 4, 6 becomes 6, negative 4. And then I get my reflection. I'm going to write it as this, only because I know it's going to be an inverse. But there's the inverse graph. So looking at the graph, you can get an idea. I'm starting everything y value below negative 2, and I'm starting x values everything to the right or equal to 2. So now when it comes to writing my equation, don't forget to include that restriction also changing x's into y's. Then we get x minus 2 is equal to the quantity of y plus 2 squared. And then we square root both sides, and we get y plus 2 is equal to plus or minus the square root of x minus 2. And then here's where we decide which one we use. I'm less than, so that means I'm using negative value. And we get y is equal to negative square root of x minus 2 minus 2 with a restriction. And once again, taking a look at the radicand, this cannot be negative. So I'm going to set this thing up to be greater than or equal to 0, which means x's must be greater than or equal to positive 2. And that needs to be included as part of my inverse. So the inverse function is negative square root of x minus 2 minus the quantity of 2, or minus 2, with a restriction on the domain of x being greater than or equal to 2. And we look at that equation, and we see that it matches this graph, because this equation has an HK of 2, negative 2, and there it is, 2, negative 2. And this equation says, make all my up and downs become downs, so I would right 1, down 1, right 4, down 2. And this says that all my x's must be greater than or equal to 2, and I can physically see that on my graph over there. Sometimes it's more helpful to take a look at drawing the reflected graph, then using that reflected graph to verify the answer on your inverse function. Now, there is a fast way to know whether a given graph is going to even generate an inverse. if your original function passes a horizontal line test. So we've looked at verticals, but we haven't seen these before. Horizontal line test. The horizontal line test tells me whether or not my graph will even have an inverse. If a horizontal line intersects your original function in one place only, then you will have an inverse. That inverse will be a function. If, in this case, my horizontal line does not intersect in just one but two places, then my reflection that I have graph-wise will not be an inverse because it won't be a function. So we would have no inverse of the equation for a parabola, whereas here in this cubic we did see that. So horizontal line test, very quick way of considering your graph and whether or not you're going to have an inverse. All right, let's look at a couple other examples. So is the inverse a function? So their terminology is a little different. We're going to draw a reflection. They're going to call that an inverse. Whether or not that inverse is a function is what this is stating. If it does, we're going to find the inverse and then graph it. Graphing-wise, again, it might be easier to see the graph. So there's our equation, f of x equals 3x minus 3x to the fifth power minus 2. So hopefully remember from our last chapter, odd degree function with a positive complete coefficient should start on the left and end on the right, upper right. Here's what the graph is going to look like. So we get that, kind of a cubic looking function. But we do see that it appears as though we're going to have an issue over down there we're at that negative 2y value. It really kind of looks like the graph is flattening out right there. But it's not. Here, let me show you. I'm going to change my properties on this, and we're going to look at x values between negative 1 and positive 1. And then I'm going to adjust my y values. We're going to go from, say, negative 1 and change my step. So let's say we went there. And it's kind of hard to see, but I'm going to change my step to something different so we can see some adjustment here. Let's say we're going to go 0.5. And I'm going to go from negative 1.5 to negative 1.9, for example. Let's see what we get. Oops. Negative 1.9. All right, it's not cooperating with me. Back to here. If I were to exaggerate this vertical scale, we would see that that actually isn't flat at that point, right where it appears to be at negative 2, even though it looks, if I were to adjust my scale a little bit, it would actually show something different than that. But so this one appears to be, it's going to pass my horizontal line test, even though, again, right in there it looks like it doesn't. That graph is actually curving more like this, going through that point of negative 2 on the y-axis. So it does pass the vertical and horizontal line test. So let's see if we can find out what its inverse equation looks like. we switch our x's and y's, and we get x minus 2 is equal to 3y to the fifth. And then divide that 3 out of there. And our y to the fifth is equal to x minus 2 over 3. And then we're going to go ahead and leave it as a fifth root of a quotient here. So there's my inverse. So there's my inverse function. And then it's an odd function, so that means I don't have to worry about negatives appearing in the radicand. I can have negative values in there, so I don't have to worry about a domain restriction. This one didn't start with a domain restriction because it was an odd function anyway. So there's that one. Let's go take a look at this next one here. Y equals 1/4 x cubed plus 3. So again, here's the graph of that. All right, take that into consideration. Again, it appears like it's getting horizontal there at y equals 3, but it's not. So this would pass the horizontal line test. If I were to then take all of the coordinates for that and reflect them, I would create my reflected graph. So let's just kind of see if we can take a look at the reflection. So 0, 3, I'm going to do something like that. At that point, it's going to be the same. It appears that I'm going through 2, 5. So 5, 2. And then another point, maybe looks like I'm almost going through 3, 10. So I'm going to just go 10, 3 just to get an idea graphing-wise what's happening here. All right. Any other helpful coordinates? It looks like maybe -2, 1. So let's go 1, -2. All right, so that's what it appears I have in terms of my reflected graph coordinate-wise. How would we enter this into our drawing of our graph? We've got all of our switched x and y points. Again, 0, 3 became 3, 0. And what appears to be around a -2, 1 became a 1, -2. So my graph is going to do something like this. And then, what's it going to do here? I come in. Wrong way. Alright, so I have my points wrong. So this 2, 5 becomes a 5, 2. And what appears to be a 3, 10 becomes a 10, 3. There we go. Makes a little more sense. So the graph's coming from this side. It appears to flatten out like it does in the example of the original function and go the other way. So that was what the inverse would look like. Equation-wise, I have 1/4 y cubed plus 3, and I get 1/4 y cubed equal to x minus 3, multiplied by 4. I get 4x minus 12 after I distribute that value, and then take that cube root, and we get 4x minus 12. So our inverse function is the cube root of 4x minus 12. There we go. So some of them a little trickier. It's easier again if you know what coordinates are. So comes to writing or graphing the reflection, just kind of look at the given coordinates of your original function and switch those around and come up with your new function. So there we go. Taking a look at our inverse and graphically how it all plays out. Hope that was helpful.